welcome Dr. Benya and Dr. Dadwal, and I wish a very happy Earth Day to all and everyone present here, all the students, scientists, and faculty members from different institutes. I welcome you all for this webinar for the celebration of Earth Day. First of all, I would like to hand over it to Dr. T.P. Singh, Director, Symbiosis Institute of Geoinformatics. Over to you, sir.
Okay, thank you, Dr. Vidya. So, in the occasion of Earth Day, they reminds us of our shared responsibility towards protecting and sustaining our planets. In this occasion, I welcome Dr. V.K. Dadwal and Dr. Mukund Devbera, eminent scientists in this area. Today's topic, satellite to soil, is a very apt as a geospatial science change that natural resource management in a many folds. As we reflect on the challenges of climate change, food security, and environmental degradations, it's become evident that science and technology must guide our path forward among these and among these geospatial technology has emerged as a powerful enablers of sustainable developments, and particularly in the field of forestry and agriculture, where we are going to be talk today, and eminent scientists they are going to be talk on this, that how we are going to save our planet Earth. Uh, and as you know, that agriculture, being the big backbone of many economies, many developing countries, including India, and it's going and a significant transformation. And traditional practices are increasingly being complemented by advanced geospatial technology or a geospatial tool. And these technologies, which include that, the remote sensing, allow us to remove towards precision agriculture. This is not only enhance, or the geospatial technology inclusion is not only enhance productivity, but also minimize environmental impacts. Geospatial data sets which we have, which we are collecting, that's basically enables real-time monitoring of crop health, and analyze that the satellite derived indices, and we can detect through that sign of stress, pest infestations, nutrition deficiency, and these timely interventions ensure better yield and reduce the risk of a large scale crop failure. In addition, I'll say that the soil mapping and spatial analysis help an efficient land and water resource management, and which is very crucial in the face of increasing climate variability. Equally, when we are talking agriculture, we look on that. The geospatial technology also important for forestry sector. Forests are, that it's a very vital ecosystem that support biodiversity, regulate climate, and act as a significant carbon sink. And today's two eminent scientists, they worked that years and years on these fields. And the technology, geospatial technology, play a crucial and critical role in the biodiversity conservations, identification of habitat or suitable habitats, identification of ecological corridors, and increasing of that, like a forest fire, satellite-based monitoring systems and work provide a near real-time alerts. Moreover, the estimation of forest biomass and the carbon stocks using geospatial technology contributes significantly to the global climate action initiatives. And today's both the scientists, they are going to be speak on those areas. On this Earth Day, the theme of a satellite to soil and resonate strong with that, the capability of geospatial technologies, and it provides us with the ability to observe the Earth in unprecedented detail, analyze of the complex environmental interactions, and make data-driven decisions. And that balance development with that, the sustainability. In this word, I pause my words over here, and I welcome to that, the two eminent scientists, and over to you, Dr. Vidya.
Thank you, sir. Thank you, sir, for setting the note for the session. Our first speaker for today's webinar is Dr. Mukunda Dev Behera. He is a professor of ecological climatology and remote sensing at the Center for Oceans, Rivers, Atmosphere and Land Sciences, Indian Institute of Technology, Kharagpur, and the founding chairperson of the Geospatial Academy. His research spans geospatial modeling, ecological climatology, forest informatics, carbon accounting, and nature-based solutions. He has made seminal contributions to forest resource management, to theory-driven modeling, satellite-based experimentation, and field measurements, developing an innovative protocols to estimate vegetation photosynthetic and structural attributes from multi-sensor Earth observation data. His work advances climate change mitigation via vegetation carbon management and NBS, with a current focus on developing digital twins at the forest monsoon climate interface over India and South Asia. Dr. Behra has authored over 170 journal papers, edited multiple books, and led more than 40 funded projects. He has served internationally, including as a review editor for IPCC AR6, mentored extensively and enabled technology transfers, strengthening India's forest and biodiversity governance following earlier service at ISRO. Thank you, sir, for accepting the invitation, and over to you for the session.
Thank you, Dr. Vidya. Let me just share the slides in a second.
Yes.
So you have to go to the screen and then
Yes, sir.
so when I have to share the entire screen, open, it is asking to open security.
Show your share option front of you.
Yes, sir.
Sir, Mukund sir,
Yes.
your share option or see that?
Yeah, I can see this arrow, share option.
Click on it.
Yeah, when I go there, yes, it has come probably. Let's see.
Okay.
Yeah, it's coming.
Yeah. Yes, sir. Yeah, we can see it.
Yeah, thank you very much, and sorry for this initial glitch. First, let me thank Symbiosis to kindly organizing this particular event on the very Earth Day today. And I'm really happy to see the online our Dr. Dadwal sir, and we'll also listen from him. So today's discussion, as I remember, when Professor Singh contacted me, he said that can you talk something on the on this aspect particularly. Just 1 second. Yeah, but particularly the forest aspect. Then I said, yes, I'll touch upon forest, but let me also talk a bit of technology which we have recently started doing. So in this way, we agreed, and today I will also talk about the digital twin as the technology, and also give you some instances what we are doing in terms of the forestry applications. So friends, I'm sure all of you in this world, particularly all of us, are working in this geospatial world, and this term like digital twin is no more new to us. But the need is, why do we need digital twin, and what purposes it serves? So the point is, we need. Uh, is this slide visible to all of you?
Yes.
Okay, thank you. So the point is, look at this. We are loaded with a lot of data. In terms of satellite data, when we have a lot of data in high temporal resolution, we have started working on time series data. So, and then we have started doing a lot of automation. Now we have lots of satellites giving us data across the domains, across what you say various resolutions, including spatial, temporal. And also we have a lot of real-time data coming from the field and various other platforms in a real-time basis through IoT and other sensors. And on the other side, we have AI technology, we have automation technology, so what not? So that means perhaps we have started thinking in terms of imitating the world, uh, uh, both based on its structural components and perhaps attributing to many of the functional components what they do perform. So coming to this, as today's discussion is going mostly on forest and agriculture, that means the two component of the broader vegetation, which we know gives or withdraws a lot of carbon dioxide from the atmosphere, and we need them to combat to deal with the recent rise and climate change and all those things. So selecting these two topics, particularly forest and agriculture, is perhaps the right thing to do in terms of the Earth Day celebration and its discussion about that. So let us see and talk about this digital twin a while. So, and try to understand what it is and why it is a bit special and different from the rest of the things. So as far as the definition goes, it is a dynamical digital representation of a physical system that is continuously updated through a real-time data exchange. So the point is, it is continuously updated through real-time data exchange. It and enables monitoring, simulation, prediction, and optimization. You can also, from this definition, we can also infer what is the difference than that of a model. So many things we are also doing this model, but what we want to say, this digital twin is perhaps a little bit more specialized in terms of integrating the data in a real-time basis. So data exchange happens through real-time basis, which because of a lot of sensors, lot of other sources of data availability is there. So the important feature is digital twins, they are evolved functionally from simple monitoring tools to intelligent smart systems. And let's go back to the history. Since 1960, when NASA used the physical and simulation-based living models during the Apollo mission to mirror the spacecraft conditions in near real time. So since then, the concept or the usage has started happening, have been noted, and we have utilized, but perhaps that term digital twin we have not given during that time. So during 2010 to 2012, the formal term adoption, particularly by NASA. So NASA Technology Roadmap formally adopted the term digital twin, especially in aerospace and high-value engineering systems. So its root first came from very high value engineering system. Something is being modeled and you try to show it in terms of a twin and in a digital space. So that digital twin word has been coined during 2010 to 12 and dominantly in engineering systems. And coming to early application, 2010 and 2015, in terms of initial implementation and the growth that accelerated due to maturity of the IoT devices. So IoT technologies, including your lot of computational, cloud computational infrastructure, big data analytics, and machine learning, all these have actually revolutionized and enabled this digital twin to move from a engineered system to a natural system. That's why we have already started working in terms of its usage in the natural ecosystems, including our vegetation and vegetation having both agriculture and forest. So what are the global challenges and relevance of digital twins? The global challenges that population growth and food security is there. You have the digital contributions, which is digital twin contribution in terms of precision farming and yield optimization. In terms of global challenge, climate change and environmental instability, and coming to the digital twin contribution, you can have the scenario simulation and adaptive planning. Coming to the biodiversity loss and ecosystem degradation, we can have various ways to monitor the ecosystem and track the carbon sequestration through the natural systems. So the implications are ecosystem restoration and sustainable forestry require transparent monitoring and performance-based system. So the difference in terms of digital twin and what do they enable and what do they support? So digital twin, they enable real-time system monitoring, data-driven decision making, and in terms of simulation before interventions, predictive analytics, closed loop automated control. As far as the various supports digital twins offer, it includes precision management, sustained intensification, climate resilience, resource efficiency, transparent and accountable ecosystems. Moving on to the various the architecture what a digital twin has, we can put it in this way. At its foundation, every digital twin architecture includes three essential elements. One is your digital connection layer, we call it digital thread, and you have the physical system at one side and the virtual, or you say the virtual system or the digital space on the other side. So physical systems, we know whatever is in the real world, and the embedded sensors and actuators, which gives us the data in terms of as far as the ecosystem or the environment is concerned. And the digital space or the virtual system includes a lot of mathematical models, AI machine learning, simulation engines, 3D visualization, and also various decision support tools. But importantly, both of them have to be connected through the digital thread in terms of continuous data exchange, real-time synchronization, and the exchange in terms of both, which we put under the feedback loop. Now, one important difference between these three terms, which we often confuse, we start with the digital models. Friends, all of us have already know about various digital models, digital elevation models, digital surface models, and terrain models, and all those things. So we put them under digital model, and we also have been using the other terminology called digital shadow. So when we take it into the digital space, we necessarily term this as the digital shadow, but which here it's a unidirectional data flow between the real and physical systems or entities are concerned. So as far as the virtual and physical entities are concerned, it is an unidirectional data flow which we put under the digital shadow. Now, in terms of the digital twin, it's a closed control loop, and there is what you say, both where the interactive data flow is there, and you have static data processing, sensor data processing, decision maker, and you have the cloud storage. So everything. So what we mean to say, we have the bidirectional cyber physical integration with autonomous decision making and, for example, smart irrigation system. So if we discuss about the layer-wise evolution of the digital architecture is concerned, you can see from a simple 3-layer digital twin in terms of physical space, virtual space, and connector, we are moving up to the extended 6-layer digital twin, which includes the physical devices, local controllers, local repositories, and also the IoT gateways, cloud-based information, and simulation and emulations. So this is what we put it under the various development as far as the architecture is concerned. So the architecture of the digital twins and the various layers. So you can see the various applications layer in terms of physical product and entities, perception layer, network layer, and application layer. So we do this in terms of our virtual space, data storage and processes, data collection, and physical space. Whereas as far as the information feedback is concerned, the simulation, modeling, analysis, and cloud computation, data storage, big data, and in using AI, and also the IoT-based sensors, drones, satellites, and remote sensing. So the main point is very clear by now that when we are loaded with data and the data storage, data analytics ability, and lot of computational power, perhaps we have started moving to digital, to make a digital twin here, particularly in terms of the ecosystem, also integrating the gradually integrating the functional aspect into that. So coming to the digital twin architecture of in terms of forest restoration, you can see here it is a kind of 4-layer digital twin architecture. So we have the physical environmental layer, the right side figure, lower right side, you can see the physical environment layer. Then the data layer from different devices, drones, and also IoT, and also the satellite. Then digital twin layer, application layer, and also the integrated system value. So data from IoT sensors, drones, and satellites are processed through the digital twin layer to generate the predictive insights. Verified outcomes recorded on blockchain, they trigger milestone-based smart contracts, and the application layer delivers monitoring dashboards, and also this the finance tools, if that is also can be integrated. So this model uniquely integrates the ecological modeling, climate finance, blockchain-based transparency, and all those what we can think of in terms of making certain decisions that helps us in managing our problem. So the generalized structure of a digital twin architecture could start from physical system, sensor IoT that gives us the data, network and data transmission, and data storage, and you have the cloud computation, edge computing, AI modeling and simulation engine, decision support and optimization, actuators control, and also the feedback to the actual or the real world system. So now, as far as the technology or enabling technology is concerned, we know we have data acquisition technology starting from IoT, remote sensing, and aerial systems, data transmission and communication infrastructure. All of us know wireless and network technology, including LoRaWAN and LP1 systems, 5G networks, the cloud computation, the edge computing, and also data storage, big data platforms in terms of computation. So digital twin manage large volume of heterogeneous data. Machine learning and AI, they are they are central to the digital twin intelligence, because this is where you give intelligence to the data, and you orient the data based on your need. You analyze the data and do intelligence analysis based on your need. So modeling and simulation technology, digital twins, they rely on hybrid modeling approaches, physical based models, data driven models, 3D visualization, and extended reality. And also you have the CPS, cyber physical networks, and AI decisions. So digital tree system is not a single technology, but an integrated ecosystem of sensing, computing, and intelligence technology. Since we are moving and we are with everything, this is the next which tries to imitate in terms of both structure and function as far as the real world is concerned. Now coming to what is our level of technological readiness? As we know, we grade it up to from 1 to 9. So we are at a different colors. They say they talk of different readiness level, and you can understand that still we are yet to achieve the ninth level, where the actual system proven in operational environment. So a lot of work needs to be done. You can say concept, prototype, and deployed stages 2, 4, and 3, and all those different stages also has been named. So the observed status, significant portions, we can say the conceptual model, TRL, technological readiness level 1 to 2. Majority of the systems are at a prototype stage. So that means we need to work a lot, and then only we can move from from a prototype to a deployed stage. So in terms of TRL status in forestry-based digital twin is concerned, it's definitely a new research domain. Mostly conceptual and early prototypes have started coming up, but no fully deployed forest scale digital twin are operational. So we need to work on this and to fully realize and take it up to a deployment stage. Now, in terms of the various attempts in forestry, we can see, let me take you to the last row in red color text. So I am digital model, digital shadow, and then digital twin. If you see this publication by Bunkor et al. At 2022, the concept, the maturity level TRL is at a conceptual stage. The physical asset in terms of forest, the data acquisition, LiDAR, soil moisture sensor, weather stations, flux tower data, the input in terms of soil, weather, tree physical and physiological processes, output, various forest management related applications, and monitoring in terms of simulation and user interface. So what I mean to say that very early attempts are there, and they are at a conceptual stage. So we need to, the system needs to move to a deployed stage where which needs a lot of work also. So a kind of conceptual case study in terms of forest digital twin framework. I'm not going to elaborate this, but it is taken from the Bincor et al. Publication by in the year 2022. So the challenges and the barriers. In terms of the challenges, data acquisition constraints. We can have sensor failures. We can have hardware cost. High hardware cost is there. Weak rural connectivity and real-time data collection difficulties. We can have other challenges such as data integration issues. There could be challenges in terms of modeling and simulation complexity. We can also have physical and virtual synchronization issues. We can have the various barriers in terms of the environmental and biological uncertainties, high cost and ROI uncertainty in terms of return of investment, infrastructure and connectivity gaps, and more importantly, the human, social, and governance level, where we feel that lack of digital skills resistance to adoption. People need to adopt it. They will say that why it is, what is the requirement when a populated country like ours, do we really need it? Then a cost benefit, resistance to adoption, just mentioned, low trust in AI. So data privacy, regulatory uncertainty, lack of digital twin standards. So what I mean to say, these challenges we can visualize in terms of opportunities, what needs to be sorted out, and to move from a low maturity to a deployment stage as far as the digital twin twin execution in a deployed stage in the real world. So the advancements are there in terms of digital twins. Now, to conclude this part, digital twin has evolved from static digital representations in terms of digital models to real-time monitoring systems, you say digital shadow, and finally to intelligent closed loop autonomous system. A true digital twin requires bidirectional data flow, in turn enabling monitoring, simulation, prediction, optimization, and autonomous control between physical and virtual systems. The architecture of digital twins has progressed from simple three-layer models to complex multi-layer and system of systems framework integrating AI, cloud-based computing, IoT, simulation engines, and governance layers. So as far as the current forestry applications, the mainly function of digital twin models, or you say digital shadows with very limited, fully integrated autonomous digital twins. Most implementation still conceptual and prototype based, and there exists no fully deployed forest scale as far as the digital twin is concerned. Now I'll take you to a very preliminary work we have also started doing in terms of developing a digital twin as far as the forest phenology is concerned over a tropical moist mixed deciduous forest. So a phenocam tower is there present, and we have the what do you say, meteorological tower also there. So what we mean to say, we get the data from the phenocam in terms of the phenological changes. We have the satellite data, we have the others, the data coming from meteorological sensors, and the field-based measurements using LiDAR systems, raster LiDAR, and also the UAV-based LiDARs. So this has thrown a challenge, and we have also taken it as a to develop a prototype as far as the digital twin of forest phenology is concerned over a tropical mixed moist deciduous forest. And this is the tower, and you have a power sensor, you have a phenocam at the top, you have solar panels, and the ATRS sensors, RAINGOs, and the various data logger systems. Also ground-based measurements we do at a seasonal frequency. This is a very high temporal resolution data we get, which actually inspired us that why not to think of developing a digital twin where the forest phenology can be taken as the theme, and if we understand this, then we can integrate into the GPP or the productivity model. So what we do, we have started doing the 3D based data collection and at various seasonal time frame, and trying to analyze the TLS based data clouds, the 3D data points, and coming with all these profiles in terms of the various tree and height and all these profiles and spatial maps, where how much and also calculating the similarity of the biomass or above ground biomass and carbon. So the point is, we have just started doing this digital twin for forest phenology over a forest type. So the message is very clear, and I must congratulate the organizers for giving me this opportunity and choosing this particular theme of forest to include and to be discussed within this forum. And As we are loaded with a lot of data coming from various sensors, including IoT devices, the cloud computations, and also the computing power, which is also given by AI, has enabled us to think the natural system over a digital platform, which we are regarding as digital twin. Thank you very much for this opportunity.
Thank you, sir. Thank you for such a motivating, and it has really motivated us to work on this digital twin and working on the simulation of the natural resource data. Thank you very much. We have our next speaker for today, Professor Vinay Kumar Dhadwal. Professor Vinay Kumar Dhadwal is currently a lead advisor science in India at Environmental Defense Fund and visiting professor at National Institute of Advanced Studies. He is widely recognized Earth observation scientist with more than 4 decades of multidisciplinary research experience. His contributions are in agriculture, land surface processes, hydrology, earth sciences, including biogeochemical cycle of carbon in India, land transformation and deforestation and disaster management, information support. His outstanding research contributions are in developing EO techniques for crop forecasting from village to national scale, assessment of the terrestrial carbon and cycle of India, forest above ground biomass mapping, vegetation productivity, and land surface processes. Professor Dadwal has 38 years of research experience in ISRO Department of Science and has held leadership positions including Director, Indian Institute of Space Science and Technology, IIST, Thiruvananthapuram, Director, National Remote Sensing Center, NRSC, ISRO, Associate Director, NRSC, Dean, Indian Institute of Remote Sensing, Dehradun, and Head Crop Inventory and Modeling Division in the Space Application Center. Concurrently, he has been Director in Charge and Deputy Director in UN Center for Space Science and Technology Education in Asia Pacific during 2009-10 and 2005-6 respectively. He was Indira Gandhi Chair Professor at National Institute of Advanced Studies during 2021 to 25. He's a fellow many academics, including International Academy of Astronautics, National Academy of Agricultural Sciences, Indian Meteorological Society, and Indian Society of Remote Sensing, Dehradun, Agrometeorological Association of India, and Astronautical Society of India. He has extensive international experience in space cooperation, including as the chair of Subcommittee on Science and Technology of UN Committee on Peaceful Usage of Outer Space at Vienna in 2016. He is a recipient of many awards and he has co-guided 15 PhD scholars in various disciplines and universities. He has chaired many committees of DST, including hyperspectral imaging and National Geospatial Program for Ministry of Agriculture and Yield Assessment for FBY, and currently is a chairman of Research Advisory Committee of National Bureau of Soil Survey and Land Use Planning. Sir, over to you, sir, for listening to you. Thank you, sir. Yeah, we can see your screen, sir. Yes, sir. Sir, if you can unmute, sir. Yes, sir. Thank you.
So, good afternoon,
Good afternoon.
all the participants, and thank you, Professor T.P. Singh, sorry, for inviting me, and Dr. Sandeepan for doing the background. and Dr. Vidya for very generous introduction. So, I am very much intrigued by the topic from satellite to soil. And Professor Behra has already covered forestry. I will try to cover agriculture. And I just in a minute, I have to get this out of it. Yeah. So here we are. You have very good social, media presence. So it promised that the all participants will get driven decision making. They will get understanding of climate smart agriculture exposure and real world sustainability applications. So what I have done is I have assumed you know remote sensing and you know geoinformatics, right? You're all students. So what I will cover is how do you extract information on agriculture from remote sensing? Then how do you detect and monitor climate smart agriculture? And then I will take some case studies on agriculture, as also soil, what work we have been doing, so that it links to CSA. Hopefully, I will try to cover it in half an hour, although I know we are a bit delayed. So, as far as the Indian agriculture and geospatial is concerned, the AIS list and NBSS were established in 50s. ISRO was established in 70s. 1980s, All State Remote Sensing Center came. Then came the Malanobis Center for Crop Forecasting. And now there are many private entities. Large number of programs are done. But there is always a capacity gap of data access, cost awareness, solutions, and scaling up. That is why all youngsters are required to really scale up the work. So the first thing about vegetation or crop is that what is the information which is seen. So in visible and NIR, you get the living cells and chlorophyll. So you can get idea of leaf area index. When you are in the near infrared range, beyond red, in the front lines, you can get the solar induced fluorescence, which allows you to see how much the absorbed photons are moving towards the chemical reaction and how many are coming back. When you move to 12 to 14 micron, you actually get the LST, thermal infrared, and there it allows you to compute the flow of water through the vegetation because that cools the vegetation and you can compute evapotranspiration. When you move to the microwave, 2 to 9 centimeter wavelength, what you get is based on X, C, L, or P, you get increasing penetration into the canopy, and that decides whether you are getting surface roughness, volume scattering biomass, soil moisture, or you can actually get something deeper about the soil. And in the passive microwave, where the surface is intrinsically giving out the long microwave radiation, there it is the water droplets in the leaf which absorb this, and you compute columnar water content or the volumetric optical depth VOD, which is equivalent to the relative water content of the leaf. So, but that was the vegetation. Then what about the soil? So soil basically uh, is related to the spectral information of the surface. It is determined by soil texture, soil moisture, soil chemistry, soil organic matter, and the erosion. Basically, smaller particles, when they erode, then the soils become brighter. And the information on soil is also very important, whether you are doing the planning, agriculture management, or making the policy. So we will touch both vegetation and soils in our lecture. Now, since we are talking of modern paradigm, so what we should also be aware is you are all familiar with UPI, right? Same way the government is, which is nothing but a financial stack of the technologies. The government is now trying to create an agri stack. So the agri stack is improve governance, have a presence-less, layer, lower the cost of agricultural services, enables scheme implementation, and accelerate innovation, right? So it has three basic registries or databases, as in geoinformatics you would have learned. There is a farmer registry, which is through his mobile number. There is a geo-referenced plot map. So each plot has a survey number, and then that is linked to the farmer. Then also every season, you collect in each plot what is sown. That is called the digital crop survey. So in India, crop surveys have been done since 1870s. But now for the first time, we are moving from the Patwari and register to a digital crop inventory. So this thing is getting rolled out. Now, once you have such a system, then you can start linking to various technologies. You have, I think, Professor Behra has already explained to you the link between the cyber physical system. Same way, uh, once you are monitoring a crop field, you can have a smart irrigation, you can have, like harvesting, you can have blockchain so that you can trace from the farm to your plate how the food has come. But you can also use this information for agriculture insurance. But for us, what is important is climate smart agriculture. So for climate smart agriculture, there are three objectives. One, we want to build the resilience and adapt to climate change. So one part of the climate change is more variability. It means more floods, more drought, more high heat events. So one has to either forecast the event or have a cropping pattern or a crop mixture which will be resilient and less loss will be there. Secondly, we have to have efficiency of irrigation and fertilizer application so that the agriculture production increases and farmers' income increases. And then the third objective of climate smart agriculture is the greenhouse gas emission, because after the use of uh, fossil fuel, the next important component of all greenhouse gas emission is agriculture. All various processes, including the methane emission and nitrous oxide emission, which are 73 and 350 times the CO2. So that is why agriculture role or agriculture contribution to GHG emission remains quite high. So this is done through, I think this was also covered in the last lecture, through hydrological modeling, through modeling of the crop, use of AI to find out best policy and intervention, and the satellite data will be giving information which I will be touching shortly. So what is the information you can get? So at the simplest, by looking at the satellite data, you can get crop land. So if you have a appropriate cloud-free data, one data, you can distinguish between crop and other land covers. So that is a cropped land. Then you can identify the crop. For identifying the crop, your spectral band should be sufficient. Two, you should have acquired data in an optimal period, or you should have multi-day data So one crop can be separated from the other with appropriate spatial resolution. The third information is crop phenology. So crop phenology comes that when do you sow the crop, when it becomes green, when it gets mature and harvest. So you require short interval repetitivity of the satellite data. Then the next information is crop rotation or cropping system. So if you follow a same point over 1 year over multiple season, so crop identification and phenology gets upgraded to a crop rotation or cropping system. These are all discriminant based, right? The next one are based on quantitative thing. So earlier we were doing pattern discrimination. Now we are trying to quantitatively assess crop figure. Various vegetation indices are there. Then to say it is a drought, what we want to do is we compare a vegetation index with a standard vegetation index, good year, bad year, or scale it. Then the LAI, for LAI, leaf area index, you should have model which can be either empirical or physical. The next stage is to have crop biomass. Again, this can be only done through model. Now, LAI and biomass are state variables, right? But photosynthesis is a process variable. So it is not only determined by the crop, but also amount of moisture, stomatal opening, the radiation which is falling, and various efficiencies. So it is a process model with added weather. And yield, so yield is basically then you have to calibrate your model or the process model with the past history, because then only the yield is a outcome of a very complex variable. So satellites are able to do this. There are hundreds of examples. I think any set remote sensing paper you see. But what I have tried to do is go on increasing the complexity of the information extracted. So, sorry, I think I pressed the wrong key. So in India, the first experiment was done 1969 in Kerala for detecting coconut wilt disease. In the phase 1, aerial data was used for crop identification. Phase 2, the production forecast and stress detection and yield modeling were done. Phase 3 was when the IRS-1C AWIFS multi-level satellite data was there. National forecasts were made. And since 2014, the Mahalanobis National Crop Forecasting Center does it. So this is the way the agriculture remote sensing has evolved in India. So this is one such example of the temporal behavior. And then you can see, you can get each pixel a profile, and that profile you know which crop, when it is sown, when it becomes. Now, if to this you add the other data like the IoT devices, the actual field boundary, and even a tree or a crop location, and then you put all the data together, you start building what will be then equivalent to agriculture digital twin. Now let us come to the soil. You may be aware India has one of the world's largest soil monitoring program, which is called Soil Health Card. Since 2015, every year, many villages are visited. So this soil health card data is truly a big data. So here in this study, some 40 million soil health card which are geolocated, they are averaged over villages. Then over that for entire country, the number of soil sample per kilometer you can see in this graphic. Somewhere there are gaps, but somewhere there are almost 1 in every hectare, or more than 200 up to those red points. Then you take proxy variable. So we have used only the soil organic carbon percentage. And then this is the national uh, distribution of SOC percent. Now this SOC percent is actually controlled by various proxies. Some 20 of them are shown here. And then this is a Shapley factor which says which are positively correlated, which are negatively correlated. This is the bar of the correlation, right? More lighter color yellowish is towards positive correlation. So what then you see is if you relate it with the all weather variable, you find out in different regions the factors which control SOC are different. So this intelligence and this understanding then allows you to really work towards the technologies and the factors which will enhance the soil organic carbon in agriculture. So this is how the process goes like. The other one is we all say that if you put more trees, you will get more soil organic carbon, which is true, but there is difference between what type of tree. So here we are comparing Kerala in some over 40-year type of a difference. All land use transitions of forest, rubber, coconut, other plantations, rice becoming to plantation, and clearing of the forest for other application. So when you put all together, so what it turned out is there are gains and there are losses. So the state of Kerala over 40 years, in spite of so much changes, forest cover, it is one of the state with highest tree cover. The net increase in soil carbon was less than 5 teragram. Right? So this was one of our recent work. Then comes the resilience. So the resilience is determined by three things: the exposure, the sensitivity, and the adaptive capacity. So the exposure based on the variability of rainfall, the sensitivity is determined by the NDVI and cropping pattern, and adaptive capacity depends upon the size of land holding, the type of soil, its water holding capacity, its fertility, and presence or absence of irrigation. So once you combine everything, you can have the vulnerability assessment or the readiness for resilience, and then do proper intervention so that all the farmers get protected. The other approach is uh, you can have fire or you can have a crop residue fire, which then releases the biomass stored carbon into the air as CO2. So the satellite data are very useful to see the counts, measure the burnt area, and with appropriate assessment, convert the burnt area and the biomass into actual CO2 emissions. Now, I explained to you the use of SIF. So generally, the first process of the CO2 fixation is gross primary productivity. Now, the satellite data are very, very useful for estimating GPP through the fraction absorbed power, and for each species, there is a separate light use efficiency, which is then degraded by a factor controlled by thermal or water stress. So how the statistical model to LUE model to a process model to a machine learning based data driven model they were, and what are the bands and the process is summarized here. So, sorry, I think. So in this study, what we did was we used the satellite data of 250-meter resolution every 15 days for about 19 years. And then for all agricultural pixels, the satellite data, the radiation, the crop type, cropland map, the weather, and the reflectance converted into water and temperature scalar, then uh, computed the GPP. Same way, over the same district, using the actual harvested crop biomass and using the inverse of harvest index, we computed what is on the ground. So now you have two estimates, a remote sensing based and a ground. So two independent estimates must match. So that is done through optimization. And then uh, one can then compute yearly what was the GPP for each agricultural pixel each year, right? So generally, what is seen is if you just take the raw products which are available, Modis or whatever, which have not been calibrated, in some areas you can have significant, over and underestimation. Modis generally underestimate the GPP over Punjab and Haryana. Right. So, okay. So then moving on to the actual yield prediction. This is a conceptual diagram where the modeling and through LAI and updating the LAI from satellite data, compute the dry matter and then partition it into this process. This has been done over hundreds of times. Now what has happened, you have getting more and more of the UAV data where you can use machine learning and other to really do a tree, every tree separate and its classification. This example is uh, over Japan, but it actually talks of what type of technologies you can use to really identify, because agroforestry is important. The other agriculture practice is shifting cultivation. Here, in this study, which was done at IIRS Dehradun, there the burning and moving from a secondary forest to crop and then abandoning and re-emergence of a secondary forest is mapped through a multi-year land trend model, which is done on the Google Earth Engine, and then you are able to create the regrowth dynamics. Regrowth is something like the resilience of the system to grow the forest, secondary forest back after the burning. This is another study which is again using high resolution data over 10 years and then using machine learning. So all trees which have big trees which have canopy of the circumference or the area of 30 square meter and above have been mapped. So basically, you find that there are 0.6 billion trees, and 11% of the trees were lost in a 10-year period, right? So 5 million trees of the size of 67 square meter of the canopy projected as seen from top, they were lost between 2018 to 22. All mappings will actually have some uncertainty. So this is a very important way to really look at the sustainability of the farmland in India. Oh my God. Every time. Sorry. This is again a study of uh, remote sensing based biomass mapping, and it uses some sample and large number of indices and multi-sensor data, both SAR as well as the optical, and then uh, have a very nice spatial map which will allow you to do the change analysis. This is another agroforestry tree mapping. Trees actually are on the field bunds. They are very important for having the biodiversity. They also act as windbreaks. The litter fall also adds to the soil, but whenever they block the light radiation near the forest, there is a reduction in the yield. So here, the stem growth is to be estimated using of the satellite data and the tree mapping for all trees outside forest. Basically, these are the agriculture scattered and burnt trees. This is a very important. They provide fuel wood, they provide fodder, and then they also take away the pressure from the other forests. So we were showing the SOC change by data. Otherwise, we can run a biosphere model. So this is a run of about 8 years of CASA, Carnegie, Ames, and Stanford model of biosphere, and where the NPP root exudate go to soil, and you have a linear order soils. So there you can see many places there is an increase. These are mostly irrigated land where there is an increase in the soil organic carbon. So we have looked at the remote sensing, but now since other data are also coming, we have also looked at the way this other heavy data, which can also be then combined in multiple ways with the satellite data to get the various drivers of change and also give the agricultural specific data solutions, right? I think I will skip this. Agriculture Foundation model and twin has already been covered. Thank you very much. If there are some queries, I'll be happy to address them. Thank you.
Participants can post their question in the chat box if they want to ask any question to the resource person.
Uh, Anyone having any question? Participants?
So a student has requested for the PPT.
Yeah.
I will mail it to Dr. Sandeepan. No issue.
Thank you, sir.
So, sir, my question: if this, now, real-time monitoring is that the one of that important aspect where that the ISRO is also planning to launch that the EOS 5, which might be provide the real-time information of data. So how much these technology development is going to be useful to identify this crop yield or identify that the exact or precise crop yield and the precise agriculture or precision agriculture better.
So now there is some clarification required here. The precision agriculture is done when you have a local sensor which senses the soil condition or the weed or lack of fertilizer, and it is linked to a machine which is called variable rate machine. It means after sensing, the machine automatically either changes the seed rate or amount of water from the hole, or it sprays a pesticide or adds more nitrogen. Now, we really do not have such type of machines, right? So it means even if you demonstrate, you can never scale it up to the nation. But what you can do instead is, if there is a field and we have an idea of last year's yield and we have a soil health card and we have this year medium range weather forecast, we can build an advisory system for the farmer when to irrigate, when to delay fertilizer application, when is the condition more conducive for pest, so he should spray. So the whole point is what works as a precision there. Here it will work in a slightly different way because our processes are manual. And the trick for the impact is to do better with what we have. Because even after so much, we now have uh, machines and harvesters, but a real-time variable rate applicator with sensor over 100 million farmer having 600 million fields is very tall order. So what we need to do now is to build, AI and machine-based advisory, so farmer can through a simple mobile can query the system and get an answer.
Okay. Here, remote sensing might be not having only the data sets which we are going to be get it. That would be only a source from a remote sensing we will get it, and that would be more on the real time, on the basis of like a phenology which is changing, or that the spectral signature which are changing at a particular area.
So you need to do that only when you are taking the decision. If you have a model that this much water was already rain or irrigated field and this is the age, so you can as we discussed through digital twin, one can be a proxy and you roughly have an idea. The satellite will be very useful after a major event. It will be useful to compare across season. It will be useful for sustainability, right? But the better data driven things, because farmer knows the crop, he knows the date of sowing, and he has a soil health card.
Okay. So other question is that that student Sharon George asking about above ground biomass depend on the wood density that varies according to species. For dense forest, how does remote sensing account for these variation, and how is a ground truthing done in this case?
Okay, so we have moved to forest. Uh, you want me to answer or Professor
Yeah,
Vera to take the question?
I think you are the better
Okay,
because you
so
worked on this. Yeah.
I'll explain to you what the traditional technique measures is the growing stock, which is volume. So you measure the girth and you measure the height, and you have a allometric equation. This allometric equation actually changes with species. So while there are published generic, but with each species there is a pressure. Then externally, this is to be multiplied by, as you correctly say, the wood volume. So generally, the one thing is you have classified as hardwood and softwood. So hardwoods may have the specific gravity 0.7, 0.75. The lighter ones, something like poplar, etc., may have 0.44, 0.45. So the type of forest and type of plantation is important. There is another issue. It is the age and girth where the specific gravity slowly changes. And when the trees become old, uh, in the core, there is death and the stem can become slightly hollow. So it means the specific gravity is a very, very highly uh, changing variable. So you have to do evidence-based data modeling for specific gravity. There could be some techniques of near stem trying to estimate the specific gravity. Otherwise, using a core borer and taking it out and taking the volume and weight is the only way. How remote sensing does it? Various forms of methods are there. You can use a lidar to get the stem volume, right? That is one way. You can use a P-band SAR, which will penetrate through leaf, etc. And the backscatter from the stems can then be scaled up to how much girth cumulative is there. The other possibility is do not go tree-wise. So what you do is you do a mixed forest plot level averaging, and then at an aggregate scale you run a model. Many times individual model running you have more error, but aggregated you can do a better prediction. So there your aim is to get in an entire range or a forest block the biomass. Generally, for ecological purpose, the aim is not to get biomass for each tree. That is only for silviculture to decide whether to cut a tree or not. So you understood. So your question must take into account your true need and the limitation of the model. Then you can do okay.
Thank you. Other question is Dr. Vidya Patkar. She is asking about what ways the digital twin will help farmer predict and mitigate the impact of climate variability on the crop yield.
Yeah, so for that, farmer may not really require digital twin. See, as Professor Behra, digital twin is when uh, data of his crop is flowing into the model and interacting. But if farmer is not collecting physical data in the sense, you only have a rain gauge, one in a gram panchayat, or you are using uh, the numerical weather prediction to find out the average temperature, or you are using only satellite data to compute the net radiation and evapotranspiration. In that case, this directly, as I was explaining, you can do aggregate total biomass GPP, convert it into NPP based on the respiration and biomass. And then if you have phenology and NPP, you know how much of it will get partitioned into the final grain yield. So that works out much better for farm level as well as village level. Village level is required for crop insurance. Farm level is required for other.
Last question is from Sahil Shah. He is asking about share some insight on the potential of a big data driven digital twin in predicting crop health dynamics under changing environmental condition in Indian context.
Yeah, so see here again, if you let us say if you want big data and that too for a crop disease, from where will it come or how will it be collected? So the only good example I know is in Andhra Pradesh. There was a German company which told farmers that if there is a disease in your groundnut or cotton, take a photograph and mail it to us. So what they did, they almost have, 1.5 lakh photographs of the diseased leaf, which they classified into what insect or what fungus it is there. So they have an AI model which can take a photograph of a leaf of known species and then break it into what is the most likely that. Now, once they have it, and then they set up a system that from wherever which lat long you get a disease, you advise what type of thing to spray. And the diseases have a way of spreading. So there are epicenter, there are loci for spreading, right? So depending upon the type of disease, etc., they could help the farmer directly without going through a twin. So in the sense, if you can shortcut the method, your aim is to advise the farmer first, detect a disease. Second, for spraying, you must ensure that the loss, economic loss, is likely to be more than the cost of spraying. Three, what is to be sprayed and what to avoid. In the sense, you can't spray if tomorrow there is going to be rain. Now you put all this together in your decision toolbox and advise. Your net result will be the reduction in the loss and farmer able to recover his crop. So what I'm saying is technologies are very good, but the decision, human intelligence, which technology to use when is also very important. One can't take a technology and apply everywhere. It will result in a lot of failures generally. That is why finally we say use community knowledge, use farmer experience, be very clear what you are doing. So while technology is good, but a blind following of technology will never be a good solution. This is my suggestion.
Yeah. Thank you, sir. Over to you, Dr. Vidya and Dr. Sandeepan.
Thank you, sir. Good afternoon, everyone. As we come to the end of today's enriching and insightful session, it is my privilege to propose the vote of thanks on the behalf of Symbiosis Institute of Geoinformatics and Symbiosis International Deemed University, Pune. I extend my heartfelt gratitude to the esteemed speakers, Dr. Mukunde Bera sir and Dr. Vinay Kumar Dadwal sir, for delivering such an insightful and thoughtful provoking sessions. The session has deepened our understanding how geospatial technology are transforming agriculture and forestry, like digital twin technology, climate smart agriculture, towards the global sustainability. Your guidance will undoubtedly inspire our students, researchers, and faculty members. I would like to express my sincere thanks to our respected Director Sir, Dr. T.P. Singh, Deputy Director Madam, Dr. Vidya Patkar, and the entire organizing team of SIG for their continuous support and dedicated efforts in successfully organizing this webinar. A special thanks to all our participants for their enthusiastic participation, engagement, and patience throughout the entire session. Before I conclude, I request all the participants to kindly fill up the feedback form posted in the chat box. Certificates will be issued within the next 15 working days. With this, we come to today's session. Thank you once again for being part of the celebration of the Earth Day. Have a wonderful day ahead. Thank you, sir. Thank you
Thank
all.
you, sir.
Okay, thank you. Thank you.
Thank you.
Thank you.
Namaskar, sir.
Sunil sir, please keep the chat box open so that the participants can fill up the feedback form.
Okay, he's already open, sir.
Okay, okay. Keep it for 5-10 minutes open.
I am asking you something. You are answering me or not?